In section 3.7, we're going to be looking at L'Hopital's rule and indeterminates. And this is one of my favorite concepts to do because it really puts together our limits, our derivatives, and it helps us to quickly work some problems that in the past we didn't have those skills to work with. And so first what I want to do is I want to talk about what is an indeterminate. An indeterminate is going to have this form of 0 divided by 0 or infinity over infinity. These are not things that we can define. They are not determinable. If you go to your calculator and type in 0 over 0, you're not going to get an answer for that. It's going to arrow message out. And then likewise with infinity over infinity. How do we define infinity over infinity? Taking a number that never stops and then also dividing it by a number that never stops. Like, how do you really define that? And so these are indeterminates. In today's concept, you're first going to determine if you have an indeterminate. If you have an indeterminate, then we're going to use this thing called L'Hopital's to help us with it. So let's look at a couple examples and then we're going to jump into what is L'Hopital's rule. And so look at this first one. If I were to take this first one, and this just goes back to, again, chapter 1, and I just straight evaluate and plug in -1, I would have 2 times -1 squared minus 2 all over -1 plus 1. So this would give me a value of 0 on top divided by 0, and I would be indeterminate. And based up our skills from chapter 1, we said, hey, we'll try some algebra with it. If you get this point, try again. And so I'm going to say the limit as x approaches -1. I'm being very careful in my notation here. I'm going to factor a 2 out of the top to give me x squared minus 1 all over x plus 1. I have not taken the limit yet, so I'm going to say the limit as x approaches -1. But in the top, I'm going to factor that as the difference of 2 squares all over x plus 1. Now I could come in here and I could say, you know what, this x plus 1 would cancel, and hopefully you remember this from chapter 1. I still have not taken the limit, so I'm going to say the limit as x approaches -1 of 2 times x minus 1. Now that I've done some algebra to reduce down this function, I can properly plug in and say, well, that's 2 times -1 plus 1, minus 1 is equal to 2 times -2, which gives me a value of -4. So in this case, I had to do some algebra to get me going before I can apply my calculus of the limit. But again, it started with straight evaluate, see if you can work it, and if not, try something else. In this case, I had a factor. And this was an example of 0 over 0. Let's look at this next example, and it is the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. This is from your previous section. If you were to just straight plug in infinities, you would get infinity over infinity. And so from our previous section, we learned that we look for the highest exponent in the denominator, and it is an x squared. And we are going to take the limit as x approaches infinity, and I'm going to divide each of these by x squared. Remember, we show all of our steps along the way. We reduce those exponents, so it gives me the limit as x approaches infinity of 3 minus 1 over x squared all over 2 plus 1 over x squared. Once you have reduced your exponents, you can then take the limit 3 minus 1 over infinity over 2 plus 1 over infinity. Remember, we show this step. We apply that concept that these turn to zeros at 1 over infinity. Again, that's relating back to our previous section. So that gives me 3 minus 0. Again, we're showing these steps. And that ends me with a result of 3 halves. So in the case of this one, I had to divide by the highest exponent. Well, what if you are in a situation and you have one of these indeterminates like we identified here in example 1 and example 2, but neither of these methods work? This is where L'Hopital's rule is going to come into play, and this is probably one of my favorite ones to do. L'Hopital's rule says this, that if the limit as x approaches c of a quotient function, that's a key part here, quotient function, f of x over g of x, that its limit is going to be equal to, under L'Hopital's rule, we put a capital L right there over that equal sign, the limit of the derivative of the top over the derivative of the bottom. Now let me make some comments here. When we are executing L'Hopital's rule, we are going to use this capital L. This is signifying why your function is changing. 2, this derivative is just the derivative of the numerator divided by just the derivative of the denominator. It is not quotient rule. Lastly, let me make a note. This limit notation is going to carry on into the next step that we have not taken that limit. So I cannot emphasize enough notation, notation, notation. And then the last thing I want to make a comment about, this only is going to work or satisfies the fact that you need to use this if you have an indeterminate form. So that's what we need to clarify. First, you have to show, do you have an indeterminate form? Then you can apply L'Hopital's rule. So the first step we're going to do is evaluate, and that should always be your first step with limits because it might work out. And so I'm going to go ahead and plug this in. This gives me e to the 2 times 0 minus 1 all over 0. Well, e to the 0 is 1, and 1 minus 1 is 0. So I do have an indeterminate of 0 over 0. So because I have an indeterminate, I can start this problem over again and use L'Hopital's rule. So I'm going to say the limit as x approaches 0 of this function. In order to apply this, I'm going to say equals under L'Hopital's rule, and you do have to put that capital L there. The limit, don't forget this notation, as x approaches 0. Now, you're going to take the derivative of just your numerator, which would be 2e to the 2x. Derivative of negative 1 is just 0. Derivative of x is 1. Now, once I took it under L'Hopital's rule, I'm going to evaluate this problem again, and that gives me 2e to the 2 times 0 over 1, which is just e to 0 is 1 times 2 gives me 2 times that 1 all over 1, so I just get a value of 2. Now, L'Hopital's rule always works if you're dealing with an indeterminate and you're taking the limit of a quotient or a rational function. If you don't have one of those two things, see what you can do to get there. Now, L'Hopital's is not a one and done type situation. You may encounter some problems where you have to apply L'Hopital's repeatedly, and that is fine because you'll note that as you're taking derivatives, sometimes those derivatives decrease in degree, and so that's going to eventually get you there to that limit. So let's look at the next example. The first thing you have to do is determine, do you have an indeterminate rational limit problem? And so I'm going to say this is the ln of infinity over infinity, which does give me infinity over infinity. You do have to show that step. So we are dealing with an indeterminate. And then I'm going to restart. The limit as x approaches infinity of ln x over x under L'Hopital's rule. I'm looking at the limit as x approaches infinity. The derivative of ln x is 1 over x. The derivative of x is just 1. Got it? Too many equal signs there. And so then this would just be equal to, notice I did not say under L'Hopital's rule because I'm not taking derivatives and applying again. I'm just cleaning up this function. And then that goes back to the previous section of 1 over infinity, so 0. And again, 0 is an okay value. It is not okay in your gas tank, your bank account, or your average for a course, but it is okay in a math problem to get 0 for a value. So again, we're going to be applying this L'Hopital's rule. Be careful of notation. You do need to keep your limit until you evaluate. Apply the capital L on top of your equal sign if you're using L'Hopital's, and you do have to show that it's indeterminate before you can jump into this. Let's do some more examples. Let's look at this next one. It says the limit as x approaches negative infinity of x squared over e to the negative x. So the first thing I'm going to do is plug it in. I get infinity squared, which is just infinity. E raised to an infinity is, again, just infinity. So I do have an indeterminate. So I'm going to start over. The limit as x approaches negative infinity of x squared over e to the negative x is equal to, under L'Hopital's rule, the limit as x approaches negative infinity, the derivative of x squared would be 2x. The derivative of e to the negative x is right e to the negative x times the derivative of your exponent, which is just negative 1. Then evaluate again. And so I look at that and I go, you know what? That's going to give me infinity over infinity again. So let's just go ahead and apply L'Hopital's again. So this is one of those problems where you can apply it again. And so that gives me the limit as x approaches negative infinity of the derivative of 2x is 2. And then on bottom, the derivative of e to the negative x is just write it times the derivative of the exponent, which is negative 1, paired with the negative we already have, just to give us positive e to the negative x. Now I think we can finally evaluate. That would be 2 over e to the negative infinity, which is 2 over infinity, which is equal to 0. But you can see in this problem, I had to apply the L'Hopital rules twice. Now, let me go back and clarify a couple things because I kind of jumped steps. Right here, when I evaluated for this e to the negative x, I was plugging in e to the negative of negative infinity. I don't think I clarified it enough that we were looking at that negative infinity. And so negative and negative would cancel. E being raised to infinite values gives you that infinite. Down here, when I plugged in the e to the negative x at negative infinity, I apologize, that should have been a positive infinity. So again, e raised to a positive number gives me that infinity I needed. Let's do another one. In the next one, it's a little bit different of a setup in the fact of it's not a rational function. So the first thing you have to do is rewrite this as a rational function and then determine if it's an indeterminate or not. And so for this next step, I'm going to say, the limit as x approaches infinity of, and I'm going to leave that square root of x on top, but since this is a negative exponent, I'm going to move it to the bottom so it becomes a positive exponent. And then we're to that point that we have an indeterminate value and we can move forward with using L'Hopital's. So I'm going to say the limit as x approaches infinity of the square root of x over e to the x equal to, under L'Hopital's, is the limit as x approaches infinity of the derivative of the square root of x would be 1/2 x to the negative 1/2. The derivative of e to the x is just e to the x. Now I'm going to clean that up, so I'm just going to say equal to the limit as x approaches infinity, because right now it doesn't look like it's going to give me a value, but I think if I manipulate and move this around, let's see, we're going to have the 1/2, we have the e to the x, and then since this is negative, I can put it on bottom, and this is really my value. So then when I go to plug in my infinity, I'm going to end up with e to the infinity, which is infinity. The square root of infinity is still infinity times 2. 1 over infinity, which is just 0. And so that worked out really nice. So don't fret if you have values of 0. That is okay. Just go slow and use your details to make sure they're accurate, and getting 0 will be okay. Now, the next question is pretty unique, and it's going to put together a lot of information. With this one, when I go and I plug it in and I plug in that infinity, I get the fact that it's going to be 1 plus 1 over infinity raised to the infinity, which is equal to 1 plus 0 to the infinity, which is 1 to infinity. And this is known as also indeterminate. Why is this one indeterminate? Because of the uniqueness of that 1 being raised to a power. We know that 1 squared is 1 and 1 cubed is 1, but 1 raised to an infinite number also falls into that value of indeterminate. So we're going to take a different approach with this function. We are going to apply L'Hopital's, but we're not ready for it yet, because although we have an indeterminate, I don't have a rational function. And really my problem is this tiny little x right here being an exponent. So whenever I have a variable as an exponent, I typically want to go into my logarithm properties. And so this is going to be a pretty neat little proof here. And so let's take the limit as x approaches infinity of this function, 1 plus 1 over x to the x. And we're going to set it equal to y, because what I want to do is I want to ln both sides so that I can pull that variable as an exponent out front. So now that I have ln of this function, we're looking at ln y equal to ln of the limit as x approaches infinity of this function. I need it equal to y so that whatever I do to one side, I can do to both. If I just ln the right side, I'm changing the function quite a bit. So I'm going to bring this x out front. And so then that's going to give me ln y equal to x times ln of the limit as x approaches infinity of 1 plus 1 over x. So that eliminated now that variable being out there. When we are working with limits, we know that coefficients can come out front or they can go inside. And so I'm going to move this limit part out in front of the xln, or absorb these xln's back in here, and that goes back to chapter 1. So I'm going to say ln y is equal to the limit as x approaches infinity of x ln of 1 plus 1 over x. And then because I have it multiplied by x, my whole goal is I want to get this set up as a rational function. And so I'm going to undo some algebra real quick. So this gives me ln y equal to the limit as x approaches infinity. I'm going to leave that ln of 1 plus 1 over x on top, and I'm going to put this x on bottom so that it's x to the negative 1 now instead of the positive 1. And so if I check here that I have a rational function of a limit, is it indeterminate? This gives me 0 over 0 when I go in and apply it, and I get that 0 on bottom because x to the negative 1 is like 1 over x. So plugging in infinity for that 1 over x gives me a 0 here. Plugging in infinity here gives me a 0. ln of 1 is 0. So this problem is an indeterminate. I don't want you to think I'm multiplying by that, but that is how we're working with this piece here. So since I have an indeterminate rational function, I can now work with that and apply L'Hopital's. And so I'm going to make another little quick fix right here, this 1 over x. I'm going to go ahead and make it x to the negative 1 as well. But again, 1 over x helps you to see it's indeterminate. X to the negative 1 is what I want to use. Now I'm going to hold tight. Just remember that this is all equal to ln y. And let's apply this equal to under L'Hopital's, and we're just working with this right side. The limit as x approaches infinity. Now the derivative of your ln x function is you put whatever you're taking the natural log of on bottom and its derivative on top, which would be negative x to the negative 2. Divide it by the derivative of x to the negative 1, which is negative x to the negative 2. Now this is a function divided by another function. So if I manipulate that and work with my fractions, like keep it, change it, flip it, I would have negative x to the negative 2 over 1 plus x to the negative 1. Keep the first fraction, change it to multiplication, and flip that second fraction. And so these actually cancel. So I have the limit as x approaches infinity of 1 over 1 plus 1 over x. And so if I take the limit of that now, I get 1 over 1 plus 1 over infinity, which is equal to 1 over 1 plus 0, which just gives me 1. But remember, this was going along for the ride. We were just manipulating that right side and applying L'Hopital. So I have ln of y equal to 1. And if I come in here and e both sides, going back to our algebra days, this would cancel, and I would get y equal to e to the first. Wow, isn't that neat? We were able to take this crazy looking limit up here, apply it under L'Hopital's. We were using our algebra skills and our calculus skills. We were able to define e. We defined what e was equal to. I felt this is like a mountaintop experience here. E is equal to the limit as x approaches infinity of 1 over 1 plus x to the x. We have defined what is E. I think that's really neat. So I wanted to show you this example, not because I'm going to throw this example on your exam, but I wanted to define E and the fact of we use E so much, but what is it really equal to? And I want to show you how your algebra skills can also help you to manipulate things and use L'Hopital's, because I don't want you to forget these skills of being able to ln both sides. And I want to expose you to these tools that you have in your back pocket that you can work through. And so I don't want you to just kind of put your blinders on and go, we're only working on Lobtails. I can't apply it here. Well, think about your algebra. Let's manipulate. Let's change things up. And so pretty neat. I think that was pretty fun. And so I wanted to just kind of work this and show you how some other skills can come into play, show you how E was defined to be. But I'm not going to put this on your test, so don't stress about that. Pretty neat proof though. Let's do another one. This one is y equals, and this will be our last example, the limit as x approaches 0 from the right of sine x to the x. And so if I straight plug into this problem, I would get sine of 0 raised to the 0 power. And this one is also described as an indeterminate. So kind of something I want to throw in there so it's not just the 0 over 0 or infinity over infinity. But I'm going to apply the same trick here like I did in the last problem. I'm going to take the limit as x approaches 0 from the right of sine x to the x, and I'm going to say it equal to y. And so in this problem, I'm going to go ahead and ln both sides because that's really the process that's going to help me to move this variable. And so I'm also going to move this variable out front, similar to the previous one. So this gives me ln y equal to x ln of the limit as x approaches 0 from the right of sine x. And just like in the previous problem, I'm going to take this x ln and go ahead and move those coefficients back in. And so it gives me ln y equal to the limit as x approaches 0 from the right of x ln of sine x. Similar to the same problem, I'm going to rewrite this as a rational function, and I'm going to go ahead and just kind of leave ln y on the left, and we'll come back and address that. So I have the limit as x approaches 0 from the right of ln of sine x. I can manipulate this x to put it in the bottom and call it x to the negative 1, or like we saw before, that is the same thing as if we wrote 1 over x, but that helps us to get it to an indeterminate form. Plugging in 0 coming from the right to your sine x is actually going to give us a negative infinity over 1 over x, which is also an infinite. And so this is indeterminate. And so now I'm going to apply this under L'Hopital's rule. And I'm going to say, let's do the limit as x approaches 0 from the right and take the derivative of the top. Don't forget your derivatives of trigs and ln's. So the derivative of ln sine x would be right what you're taking the natural log of, on top the derivative of sine x, which would be cosine x. The derivative of that 1 over x is negative 1 over x squared, or negative x to the negative 2 if you prefer. Can't forget all your trig functions. This is the limit as x approaches 0 from the right of cosine over sine, which is cotangent, over negative 1 over x squared. I do want to evaluate this limit, so I'm going to bump this back up. And so this gives me the limit as x approaches 0 from the right of negative x squared cotangent x. And cotangent, if I move it to the bottom, gives me negative x squared over tangent x. And the limit of negative x squared over tangent x is 0 over 0. So again, we're at a place of indeterminate. So we're going to apply this under L'Hopital's again. The limit as x approaches 0 from the right of derivative of the top would be negative 2x. The derivative of tangent x is secant squared x, going back to our trig days. And if I apply this and plug in my zeros, this gives me equal to negative 2 over 0 times secant squared of 0. I'm going to go ahead and bring down this ln y. So I get ln of y is equal to 0 over 1. And similar to the last problem, I'm going to e both sides. So this would cancel. And I have y equal to e to the 0 power, which is equal to 1. Therefore, the limit as x approaches 0 from the right of sine x to the x is equal to 1. So again, Pretty neat little proof there. We're putting a lot of concepts together. Algebra helped us with that. And Lobtail's repeatedly also was of assistance. You also had to be keen on your trig problems. So again, I'm not going to put an example like this on the test, but I want to expose you to all these concepts and knowledges and building blocks that you have throughout your math education and how it can all come together using one of these concepts. And so pretty neat. If you need some additional assistance with 3.7, please just reach out through Canvas messaging.